This paper is about using strategy logic for automated verification of mechanisms, and it's a joint work with Bastien, Aniello, and Laurent. In the problem of mechanism design, we have a set of agents, each one with a preference over a decision we need to make. And the challenge is designing a game or a mechanism that will aggregate the agent's reported preferences or the agent's strategies in a decision. The designer of such game may also have a number of objectives in relation to the desirable behavior of the players, and also in relation to desirable features of the outcome. So for instance, an objective could be that the agents have an incentive for participating. Other objective could be that the agents do not have a reason for lying about their preferences. And also in relation to the outcome, we may want that the mechanism does not lose money. Usually, verifying whether a mechanism has a number of properties is proved by hand, which may be difficult and time-consuming. So in this paper, our idea is to propose using a logic-based language for doing the verification of such properties. For doing so, we have a number of requirements. First, we need to be able to handle quantitative aspects, as the outcome of mechanisms may involve payments, and also we need to consider utilities and so on. Second, we need to consider the setting of imperfect information, as the agent's preferences may not be known by other agents. And finally, for evaluating these mechanisms, we need to be able to express complex solution concepts such as Nash equilibrium. For addressing all these three requirements, we propose a quantitative and epistemic version of strategy logic, which we denote SLKF. The semantics of SLKF are based on weighted concurrent game structures, which are similar to the structures used by standard strategy logic. However, we also consider a weight function which assigns a value between -1 to 1 to each atomic proposition in each state of the game. In this paper, we also consider the concepts of strategies and assignments, in which strategies for an agent is a mapping from the game states into actions, and an assignment means a mapping from agents and variables into strategies. The syntax of SLKF is the following, where we have an existential quantificator of various strategies that is reading the resistance and strategy S for agent A such that 5. We also have binding, whose meaning is that when we bind to the agent A the strategy SA, 5 holds. We have an knowledge operator with the standard meaning, and 2 temporal operators denoting next and until. Finally, we consider a set of functions whose control domain is in -1 to 1, and we may write them in the language. In the case where the atomic propositions only take values +1 denoting false and 1 denoting true, and the functions we are considering are the ones representing negation and disjunction, then SLKF corresponds to the usual Boolean evaluated strategy logic with an epistemic operator. In relation to the semantics, we evaluate the satisfaction value of a formula phi in a state V, which will be also weighted from -1 to 1. For giving an idea, so the formula, there exists this strategy as A such that phi will have the maximum value for phi for all strategy sigma when we assign to the variable SA the strategy sigma. And for binding, it will have the value of phi when we assign to the agent A the variable assigned to the strategy assigned to variable SA. With SLKF, we can encode a number of solution concepts. So for instance, we have that the strategy profile is an Nash equilibrium when no agent can improve her utility by doing an unilateral change of strategy. So we can write for all agents and all alternative strategies T. When the agent binds to the strategy T, she cannot achieve an utility that is greater than if she had followed the strategy in S. Similarly, we also show in our paper how to consider dominant strategy equilibrium. Now I'm going to talk how can we consider concepts from mechanism design with this language. So first, consider that we have a set of alternatives, and we also have the agent's type, which denote the preference of the agents over the set of alternatives. A social choice function is a mapping from the agent's type profile into alternatives. In this work, we consider that a concurrent game structure is representing a mechanism in which we have atomic propositions for describing the alternatives. Given an equilibrium notion, we say that a mechanism is implementing a social choice function if they assign the same alternative in some equilibrium for any type profile the agents may have. Now I'm going to illustrate how can we encode a property from a mechanism. And for instance, individual rationality means that the agents can achieve an utility of at least 0. And we encode the condition of having an utility greater than 0 through an SLKF formula. And in our paper, we show that a social choice function is individual rational when the formula IR has the satisfaction value in 1 in the equilibrium where the concurrent game structure is implementing this social choice function. Other property of interest is the one of strategic proofness that denotes the agents cannot improve their utility by reporting a fake preference. And we show that the mechanism is strategy proof when the strategy profile in which each agent truthfully reports the preference is a dominant strategy equilibrium. That means the satisfaction value is 1. In our paper, we also describe how to consider efficiency, Pareto optimality, budget balance, and a revenue benchmark that is based on the agent's knowledge. In relation to the complexity, if we assume that the functions we are considering can be computed in polynomial space, then the model checking of the language is p-space complete with memorialized agents. In conclusion, we propose this language SLKF, and we show how to model and consider concepts from mechanism design. Verifying properties from mechanisms then boils down to model checking SLKF formulas. For future work, we want to consider the probabilistic setting with mixed strategies, and also the synthesis of mechanisms from their logical description. Thank you for listening.